Hey everyone, we're going to continue looking at the 2018 3.4 examination paper. Let's move on to question 2. Okay, so question 2, alright, so this is a intermolecular force type of question because as soon as you see tables like this with the molar masses and then the enthalpy change or the melting point, boiling point, whatever, that's the same type of question. It's intermolecular forces. Okay, so this is a quite big part of the topic. So first thing first, you need to identify what it has. So if you look at this, it has O bonding to H. So this has hydrogen bonding straight away. And it also has permanent dipole-dipole. If you have hydrogen bonding, you can have permanent dipole-dipole force of attraction. And something I should have done at the beginning is that all three of them, I'm not going to write them individually, all three, any molecules that you see, all of them have temporary dipole-dipole force of attraction. Okay, so just write that down straight away. Now propan 1O, same thing. This has also have hydrogen bonding. I'm just going to be, I'll just write the whole thing, hydrogen bonding, and then also permanent dipole-dipole force of attraction, because whenever you have a oxygen bonded to a hydrogen or nitrogen or fluorine, then you have hydrogen bonding. Propanol does only have permanent dipole-dipole force of attraction. So this is a very, so if you're good at organic, then you should know that your aldehyde don't have hydrogen bonding. Okay, compare and contrast the enthalpy of vaporization of these. The answer shows explanation of the relative strength and attractive forces. Okay, so when we're talking about these, as you can see, quite a bit of answers underneath. So let's just break it down. So first thing first, what is the most, what's the most, the highest, the strongest molecule in terms of the intermolecular forces? It should be this one because it has the highest enthalpy change. Okay, why is that? It has two things. First of all, it has the largest molar mass compared to the other two. So that will have the strongest temporary dipole-dipole force of attraction. So temporary dipole-dipole force of attraction is due to the random movement of the electrons. So if they have a molar, if you have a bigger molar mass, that means you have more electrons. If you have more electrons, that will make the molecule more polarizable, and that will result in stronger temporary dipoles, and that will result in stronger temporary dipole-dipole force of attraction. Okay, so for your propan 1O that has the strongest temporary dipole, I mean this one's quite similar, but this one, like if I verse methanol versus propan 1O, the propan 1O will win because yes, both of them have hydrogen bonding and permanent dipole-dipole force attraction, but propan 1O has a stronger in temporary dipole-dipole force attraction due to the larger molar mass. This is why 47 is greater than 38. Okay, so that's how it wins. Now, if we compare 47 to 30, yes, they have similar sort of molar mass, so they have similar temporary dipole-dipole force of attraction, but because propan now doesn't have hydrogen bonding, so it loses out, and then you have got a stronger melting point, as you know, in this case vaporization enthalpy change in propan 1O compared to propanol. If I compare methanol to propanol, the methanol has a higher enthalpy of the change of enthalpy of vaporization, because despite having a lower molar mass, it has hydrogen bonding, which is strongest intermolecular force. That's why it takes more energy to break those. Okay, so it really depends on how you want to structure these answers. I normally want my students to kind of explain what type of intermolecular forces that we're talking about. Like say temporary dipole-dipole force of attraction is due to movement of electron densities, and then the hydrogen bonding, you know, sometimes I ask them to draw a diagram, you know, but you can explain this in whatever way you want. So in this case, they just broke it down into pairs, like I kind of mentioned. So methanol, propan 1O have temporary dipole hydrogen bonding, but because propan 1O has larger electron cloud than methanol, because of the larger molar mass, it has a stronger temporary dipole force attraction, therefore high enthalpy of vaporization, because it requires more energy to overcome the intermolecular forces. Now, if we look at propanol and propan 1O, and this has a lower enthalpy vaporization because it just doesn't have hydrogen bonding, which is the strongest intermolecular force, but it doesn't have it, so it's the weakest one. Okay, but propanol, propanol have electron clouds of the same size, so it's going to the second comparison I kind of did. So they have the same sort of molar mass, but because it doesn't have hydrogen bonding, it's going to be the weakest molecule in terms of the intermolecular forces. Okay, so that's a very, very typical question, guys. I mean, if you go through the past, I don't know, 5 years of exams, you're gonna find questions like this every single year. This isn't guaranteed excellence question. Grind it, make sure you can do it. Definitely worth your time. Okay, definitely worth your time. Let's move on to the next one. Calculation. Okay, so we want to calculate the enthalpy of combustion for this equation. Now, this is a trick. Can you guys see we got all enthalpy of formation? So you're going to remember that enthalpy of reaction is going to be the total of enthalpy of formation of products minus the total of enthalpy of formation of reactants. Okay, so in this case it's delta H, it doesn't really matter. So the enthalpy formation of products, what are my products? These are my products, so it will be 3 times CO2, which is 394 right here, 4 times water, which is negative 286 right here. So that's my enthalpy of products minus the enthalpy reaction, enthalpy of products of reactants, which is 1 mole of that. So it's just negative 255. And then O2 doesn't have an enthalpy of formation because the formation enthalpy of formation definition is the amount of energy released or required when you make 1 mole of molecule from its constituent elements. This is already an element. So to make an element from an element, you require no enthalpy. So if you crunch these numbers in your calculators, you get negative 2071 kilojoules per mole. And just good habit, always round to 3SF, negative 2070 kilojoules per mole. 3 significant figures. Okay, nice and easy, only merit. Next one. Explain why enthalpy combustion of propanol would differ if water was produced as a gas rather than liquid. So you are trying to turn or differ if water is produced as a gas rather than liquid. So if you produce water as a liquid versus a gas, you would require less, the enthalpy change will be less because you need to convert your liquid to the gas, and in this process energy will be absorbed. Energy has to be absorbed in order for this to happen. Okay, so you can't, because this is a state change whenever you're trying to going from liquid to gas, so we have to, why is the energy absorbed? Because we have to overcome intermolecular forces. So if you go back to this question here, that's talking about water liquid, and they're saying we want to turn into gaseous H2O. So you have to spend some of the energy released. You won't release that much energy because some of it would have been consumed to turn this liquid water into gaseous water, and then the energy can be released. So you obviously lose less energy. Okay, hopefully that makes sense. This is just a mirror question, so enthalpy will be less negative or less exothermic because you just don't release as much energy. Where did that energy go? Because that bit of energy is being absorbed to break the intermolecular force of attraction to turn liquid to gas. Okay, so therefore you're releasing less heat energy because that heat energy has gone to make this process happen. Okay, hopefully this one makes sense. Oh, Hess's law calculation, I believe that's it. Yes, this is my favorite type of question. It's like simultaneous equations. So calculate the enthalpy. All right, so this is my equation of interest. I want to rearrange my equation, so I'm just going to number 1, 2, 3, 4. I want to rearrange these bad boys so I can cancel them out, and then come up with these. Okay, so first thing first, I don't even look at these things underneath. I don't even look at them. I just look at these individually. I need 2 aluminium solids on the left hand side. Which one has aluminium? Right here. So this is the only one that has aluminium. Let's just double check. There's no aluminium. Yep, there's no aluminium. So number 1, done. Don't need to do it. Aluminium, tick, done. Now I need 3 Cl2 gas. Cl2 gas. Oh, there it is. There's a Cl2 gas right there, and that's the only Cl2 gas I need. So I need to use number 2 multiply by 3, and that will give me 3H2 gaseous plus 3 Cl2 gaseous turns into 6 HCl. Everything's multiplied by 3, and that'll be 184 negative times 3. And then I have my 3Cl2. I need 1 Cl6 on the right hand side, but this one is solid. Okay, so I need a solid. I have an aqueous here. So what we want is that we want the solid on this side, so we need to reverse. Oh, hold on. Before we get there, I just noticed that there's state difference. No, not yet. Not just keep going. Let's just do it how I will do it. All right. So number 4. Let's reverse number 4. Reverse number 4. Why do we need to reverse it? Because we need Al2Cl. We need the solid stuff on the right hand side. So it's Al2Cl6. Oops, I say 6. I write 3. Don't you love it? Aqueous turning into Al2Cl6 solid, and that will be positive 643. Okay, now and then you have this reaction number 3. Then you're like, this doesn't make sense. Why is this reaction given? We don't give equations for no reason now, because I can sort of see it straight away because I've done it so many times. Is that, can you roughly see that? I'm just going to quickly highlight it. I can't delete this, so that's going to stay. Can you see the Al2Cl2 aqueous that it's highlighted is going to cancel out with this Al2Cl6 aqueous on the right hand side? So these guys will go. Can you see the I have a problem in my reaction. I have no HCl aqueous, so I need to get rid of these guys somehow. How do I get rid of them? Is I need to have 6 HCl aqueous on the right hand side, and if I multiply, I'm just going to use a different color pen. If I multiply this guy by 6, so this has to go by 6. And remember what we did for reaction number 2. Can you see that 6 HCl gaseous over here is cancelled out by this 6 HCl gaseous over here? So that perfectly works out. So this is where experience comes into play, and this is just by grinding a lot of questions. So compared to the 2019 question, I think I remember quite vividly, it was quite easy. This one is actually quite challenging, which is quite good if you ask me, because 3 equations. Hess's law is just too easy. Very standard. This is more of a challenge. So we have to, number 3, we have to multiply by 6 because we want to have 6 HCl aqueous on the right hand side. 6 HCl aqueous, and that will be negative 72.4 times 6. Okay, let's just write the first equation up here. 2Al, I'm just going to copy the first equation here so we can see my favorite part of Hess's law, which is just deleting everything. Aqueous plus 3H2 gas. Okay, so here we go. So can you see that 3H2 gas? That's cancelled. That's 6 HCl aqueous, cancelled. That's 6 HCl gas, cancelled. That's 3 Cl2, I need that. Al2, nope, I got everything that's left. So this thing right here is that. Cl2 gaseous is right there. Al2Cl6 Cl6 solid is there. So that just shows I've done everything correctly. So what do I do with the final answer? The final answer will be negative 1003, which is this enthalpy, plus negative 184 times 3, which is this enthalpy, plus 643, which is this enthalpy change, plus negative 72.4 times 6, which is this enthalpy change, and that is going to give me negative 1350 kilojoules per mole. 3 significant figures. Okay, so with Hess's law, because with the easier ones, I don't even write, you know, this times 2, times 3 stuff. I can just see it straight away. I just go with start playing with the numbers. But this one, you actually have to think about it. You have to look for, like, especially with the first reaction, because once you just, you know, when I start ticking it, that means I can't change it anymore. I have to keep it. So how do I get rid of this 6HCl aqueous? Well, you can only do that by playing with this third equation here, which is that part. Okay, so that just comes with a bit of experience. But yeah, that's question 2, and we'll move on to question 3 for the next video. So hope you've been finding this video helpful. Subscribe if you haven't, and smash the like button, and we'll see you guys next time. Bye bye.